Thank you very much, Scott. So yes, that's the title, Invariants. Bounded and perfect complexes. And when I first learned about this workshop, I thought it would be fairly easy to give a talk that just avoided the topic of the workshop completely. But then, when actually reading the workshop description and also being here and seeing the diversity of talks here, I realized it's not as easy as I thought. So I did not manage completely to avoid it. Right. So the other thing I should say before I start is that this is all based on joint work with Sira Gratz, penko, and Stevenson. And actually this is kind of a little bit of a hobby project that I'm going to talk about today. Back when we were here as a working group at a junior trimester program 2 years ago. So that's part of what we did. And I have to say that being back here really increases the, maybe let's call it motivation, to finally bring some of that stuff we did out to the public, and that's the first step in that direction. Right, so what we're going to do throughout the talk is we're going to fix some field K, and we're going to fix a finite dimensional algebra over K. So that's going to remain throughout the talk. And as the title suggests, we have two main players today. First, we have the derived category of perfect complexes of lambda. So these are just the perfect complexes, i.e. The bounded complexes of finitely generated projective modules. So that's just KB, small proj, lambda. Right. The other star of today's talk is the bounded derived category of lambda. So these are just the EV mod lambda. I'm just writing EV lambda for short. So these are the bounded complexes of finitely generated modules. And the point is that these two guys are very closely related to one another. They know a lot about each other. And what we always have is, right, we sit within the whole derived category of all the lambda modules, and in there, maybe that saves a bit of space. Within there, we have the bounded derived category, dB lambda. Now we work over a finite dimensional algebra, so we can just describe that as the finite derived category. So all the guys sitting in my whole derived category that have finite dimensional total cohomology. Within there, I have my perfect complexes, right? Not all finitely generated. Bounded complexes, just the ones made up of finitely generated projectives. And so I can just think of that as the smallest thick subcategory containing lambda itself as a module over itself, which is just, I can describe intrinsically as just the compact objects within my derived category. So that's what we have. And yeah, we were interested in this relationship from a certain perspective. And occasionally, right, it happens that we actually have equality here. So we have that these categories are the same. dperf is equal to dB lambda, and that happens if and only if the global dimension of our algebra lambda is finite, which just means that all the simples have finite projective dimension. And now the point that's kind of important to us actually is, right, because we work over finite dimensional algebras, the simples generate a bounded derived category, right? So if they are already in here, then everything is just equal. Okay, very good. Now, in any case, even if they're not all the nodes the same, which for us today would be a little bit boring, we want something a bit more fun to happen from that perspective. But even if they're not the same, then I'm not sure if you can read that with the shadow, but in any case, dB lambda and dperf lambda are closely connected, or closely related, not a technical term. They determine each other. So there are several ways one could see that we can get from one to the other and back. For example, and I guess this goes back to Rickert, we can, well, we could start, right, we could say we have the derived category of perfect complexes that's intrinsically described. How do I now from this get my bounded derived category? And in fact, this is basically just restating how we defined it up here. We can write dB lambda in terms of dperf lambda by just considering homomorphism. So, namely, dB lambda is just all of my objects, or the full subcategory of all the objects in the whole derived category, such that we take our hom into such an object. Thank you. And we restrict that thing to the category of perfect complexes that we know, right? So we want to start. Then this functor has image in, doesn't write that because it takes a lot, has image in not just anywhere in the derived category of vector spaces, but in the perfect derived category of vector spaces. dperf k. So I can write it that way. I see that my dperf lambda determines dB lambda in that way. You can also go back. You could write dperf lambda analogously in terms of dB lambda as just being all the object in the derived category, such that if you take our hom out of these and you restrict to what we start with, dB lambda, then this has image in the same subcategory, image in dperf of k. So this would be one way to see that these actually determine one another. Now, there is more recent work. I should mention Henning Krause and Amnon Nehmer. And those of you who were lucky enough to be around for Amnon's series of talks, you will have a much more intimate knowledge of this, what I'm going to mention here in the talk. But we can actually using completion, and that falls out as a special case in both of these words, we can view dB lambda as an approximation of stuff in the perfect complexes. So we can approximate dB lambda by a perfect complex. Now, I understand that this talk is gonna go on YouTube eventually, if I give the permission, and that means it's just suitable to have a bit of a commercial break at this point. And the commercial break is that if you are interested in learning more about these, we're gonna have a masterclass in Aarhus. So maybe I'm going to just say, I'm not going to say anything more about this, I'm just going to say CF. This is the CCC masterclass in Aarhus in March 2023. And we're lucky enough to have both Henning and Amnon as speakers there. And this CCC stands for categories, clusters, and completions. And for the clusters, so for the second C, we have Shooting Sue responsible for that. All right. So, yes, commercial break over. So the point of today's talk is though that we kind of handwave and said yes. I mean, not just handwave as opposed to explicitly write something down, but we see like these really understand one another. Oh, delicate. Yeah, they really have a good understanding of one another. They're really closely related. And the theme of the talk is basically how well do invariants notice that relationship. So you could maybe frame that positively or negatively. You could say which invariants are brutal enough to not notice that these are actually different categories. Or you could say, well, which invariants are clever enough to know that they're actually really closely related. So the point is that some invariants reflect this. So some invariants reflect this idea that we can get from one to the other in formal ways. And as an example, we can look at Hausdorff cohomology. And this result is due to Lowen and Vandenberg. And what they tell us is that Hausdorff cohomology of the perf of lambda, well, this is actually just Hausdorff cohomology of lambda. And in particular here, when we have a finite dimensional algebra lambda, then this is isomorphic to Hausdorff cohomology of dB lambda. Now, that...
Are you enhancing, yes?
Yes. Oh, sorry, maybe I'm just secretly working with enhancement. Or maybe not so secretly in a little bit. So this might initially.
It won't be secret if it's on YouTube. You know, so.
Oh yeah, that's true. That's a good point. I should have given that away. So I'm openly working with enhancements. Good. So this might initially be a surprising result. It's pretty cool. Pretty cool result. The whole completion stuff that came later, right? But if we, so this is not by all means going to be a formal proof of this, but if we believe this kind of idea that we can approximate dB lambda through perfect complexes, we can give a little bit of a plausibility argument for that. So if we want to compute the self-extension of the identity factor of dB lambda, right? So this is just given pointwise on all the objects. But every object in dB lambda, we can approximate arbitrarily well by some perfect complexes, right? So this is going to come from some maps and pointwise on the perfect complexes. Now, this tells us, and one has to check the naturality and stuff, but this tells us that we can actually glue together this self-extension of the identity functor here from self-extension of the identity functor down here. So that can give us a bit of a philosophical idea of why this result now seems maybe fairly plausible if we think of it in terms of this completion business. Okay. So this is a pretty good start. So we have some nice important invariants that do not detect the difference between the two. So we could perhaps get a bit carried away and ask the question, how differently do invariants see dB, lambda, and dperf lambda? And you might say that's a very general question. Surely that's a bad question, Sira. And you would be right, it is much too general. So this is we can't say anything about this in this generality. So there's some invariants that see this, some invariants that don't see this. So let's look at some examples.
One question?
Yes.
By invariant, do you mean additive invariant?
Well, I mean, I want to group Hausdorff cohomology under here as well, which is not even functorial. But so I mean, I guess later. So later we're gonna restrict ourselves to a nice class of invariants. I mean, I guess yes. No, sorry. I guess yes. Yeah. Later, I'm gonna restrict myself to
Okay, so in this thing, there's no obvious map here, right, between the two? Or
Restriction.
well, I mean, yes. I mean, that would be kind of the idea.
dB lambda is contained. Deep lambda is contained, and so you can restrict Hausdorff cycle on dB lambda to dB.
Exactly. So that's kind of
the Hausdorff cohomology of the stable category, for instance, would be what? Would be 0 or would be?
Well, I mean, no, because it's not functorial. I mean, it's not. Yeah.
That's just.
No, I mean, the way they. I mean, I'm not overly familiar with their proof, but I know it's completely different and not using any of these ideas. So I don't know if they explicitly construct. Okay. Good. All right. So some more examples.
Maybe a remark. I mean, for Hausdorff homology, they are in duality, as you're probably going to say. Sorry.
Don't take away my talk, then. So first, let's start with something that it still makes us a bit more optimistic about the non-distinguishing thing. So let's look at K0. Yes. So K0 of the perfect derived category. So what is that thing? Well, the perfect derived category is generated by lambda, or it's generated by all the indecomposable projectives. Right, and let's say we have n of those. Let's say n is the number of isoclasses of simple lambda modules which coincides with the number of isoclasses of indecomposable projectives. Now, the indecomposable projective generate that thing, and they actually generate the Grothendieck group, and they do that freely. So K0 of dperf is just Z to D. Now, if we look at K0 of dB lambda, now this guy is generated by the simple modules, but there's again n of those, or n isoclasses at least, of those, and again, they're free. So this is again z to the n. Okay, so they agree. Nice. Now, an interesting question one could ask here is that what is the induced map between them? So the map coming from the inclusion. So we have that the path includes into dB lambda. So that should give us some sort of map between the z ends. And we're just going to do some hand waving around. But well, what we know is, right, we have chosen this basis, right? Here is a basis of indecomposable projectives, and here it's a basis of simples. And what does inclusion do? It just sends the projectives, well, to the projectives. But we now want to express them in terms of the simples, right? So we want to write a class of an indecomposable projective in terms of a linear combination of the classes of simples. And the thing that does that, the matrix that describes this map is just the Cartan matrix. Yeah, so this thing is the Cartan matrix, which is just base change from indecomposable projectives to simples. Then we're going to come back to that matrix later on. So its column vectors are just going to be the dimension vectors of the indecomposable.
Base change and basis change, is that the same?
Oh,
Yes.
should be, sorry. Well, we changed the basis. Oh, base, should it be basis change? Well, there's two bases, right? So we're going to have a basis change. Well, I guess we changed the basis, so yeah, well, whatever. I guess it should be singular. We're going to just leave it. Alright, so far we're pretty hopeful, everything agrees, and in light of, in the spirit of this morning's talk by Anna, we could even say, well, let's look at negative character theory. That for I bigger than 0, or k minus I of the path lambda, well, that's just k minus I of lambda, and one can show that this vanishes. So that's 0. And of course, after today, you know what happens for dB. Right, that guy has a bounded T-structure with a theory part, so this vanishes as well. So really good, the stuff still agrees. But we should not get carried away by that because of what Ben had said before, which is like, what if we look at Hausdorff homology? However, Hausdorff homology does not agree in general. So, for example, maybe one could, yeah. Example, look at the dual numbers. So k epsilon, where epsilon squares to 0. Then Hausdorff homology of the perf of lambda. Well, this is an additive invariant. This is a localizing invariant. This is the same as Hausdorff homology of lambda itself. So Hausdorff homology of a algebra is going to be concentrated in non-negative degrees. And in fact, well, you can just directly compute that, it is non-vanishing in infinitely many positive degrees, in fact in all, well, non-negative degrees in all of them. It's like non-trivial in infinitely many degrees. Now, on the other hand, if we look at Hausdorff homology of dB lambda, then, well, one can actually show that this is just dual to that side. So that thing is now going to be concentrated in non-positive degrees. And yes, in fact, so these are very much not the same, right? Very different, but they're still related. They're dual to one another. And I'm aware that this is true in this example, and I'm like aware that it's kind of plausible to think that this is always true. But in light of what Bernhard asked me earlier, let me ask back. Do you know that this is true in general?
How general do you know?
Well, I don't know. In what generality do we know it?
These two categories are causal to each other.
Yes.
We know it.
Oh, okay. That is fine. That is fine with me. Okay. But I mean, like, kind of, it's kind of an interesting question in like what generality would that hold, right? Somehow because you can think of d perf and dB lambda to be dual to one another on a dg level. So does that mean that Hausdorff homology actually sees that duality? And I don't know how generally this is true, but I think this would be quite an interesting question, because maybe it gives us a way to reframe Hans' conjecture as well in that term. Yes. But in that case, yes, definitely, they're dual to one another. So Hausdorff homology still sees the relation. But just not on the nose, it's not equal. Fantastic, so what can we say, right? We've seen that different invariants see this stuff quite differently, so is there even a statement we can make? And like luckily, right, for me there is something that I can tell you. And this is our theorem. I count the alphabet. First grammar, no alphabet, it's hard. Okay.
Is this thing with the hat before the one without the hat?
No, I mean, like, I don't know where that, I mean, that, I'm not going to go into Slovenian alphabet, I don't know where that shows up. I count it as yes. Okay, so, I'll have to ask Spela about that, yes, so. Good, so, now, the thing is that we need an assumption here. And in a way, you could say it's a bit sad that we need an assumption, and every other day I would agree with you. But today I'm going to say it's lucky for me that we need an assumption, because this is my slight flirtation with equivariance today. So that's how I fit into this conference. So we have our finite dimensional algebra, and what we need to assume for our proof is that let lambda admit a nice grading. So what we want is a non-negative Z grading, right? Non-negative grading, such that lambda 0 is semi-simple. So that's our hypothesis Then what we can say, there is a class of invariants that does not see the difference between dB lambda and d per lambda. And that class of invariants, I'm going to talk about that pretty soon after I state the theorem. So let E, B, and A1 homotopy invariant, then E does not see the difference between our stars. So E of dB lambda is isomorphic to E of d per lambda. Now, I'm not saying that we need this hypothesis for the statement to be true. In fact, I hope this is not the case, but we do rely on it for the proof. And the first thing maybe I want to point out is that it really is a hypothesis, so we don't get that for free, even in like small examples.
You would first tell us what the A1 homotopy is?
Yes, yes. So let me just allow me to be capricious here and first tell you why we need, why the hypothesis is a hypothesis, and then straight away I'll tell you what an A1 homotopy invariant is, or I'll describe it, maybe. Okay. So, firstly, let's analyze what's up here. First, let's just start with the start. Let me be that my excuse. And we have, so the gradability, I'm not sure why I got a strange symbol, gradability, ability is a hypothesis. And I need my notes now. There is, so there are algebras, even small dimensional algebras, that are not gradable in such a way. And the example that I'm aware of is due to Belzner, Burgess, Fuller, and Schulz. And they give us an algebra. So that's, for example, with two generators, x and y, subject to a short list of relations, x cubed, xy, yx squared, x squared minus y cubed, and yx minus y cubed. Oh. Copy anything wrong? No, it seems to be correct. So that thing is a 5-dimensional algebra. It's nice, it's local, it's self-injective, but it does not admit a semi-simple gradient, positive, non-negative semi-simple gradient, which does not allow such a gradient.
Any group of order 8 is another nice example.
Good. Bigger though.
Yeah.
And then you want to give us an invariant that does not distinguish perf from
Yes. Exactly.
Sorry.
You really.
You got distracted by it.
It's gonna happen. It's gonna happen now.
Yeah.
So an A1 homotopy invariant.
No, I mean, I'm not sure I understand what you mean by this. If you want to say it's a necessary hypothesis, you need to give us an invariant that does not distinguish.
Oh
like
no!
the
Okay, no. Okay, no. Maybe I didn't express myself very clearly. It is absolutely necessary for the proof we have. I don't think, I'm going to be bold, right? We're going to say that on YouTube. It is not clear that we need that hypothesis. In fact, it would be really, really nice if we could just drop it. Maybe I'll talk a bit about that, but now, so it would be super interesting to have a structural proof of that. We just don't have one. And kind of part of why it would be really nice is to really maybe one could really think of this again as the fact that these determine one another, right? And can be viewed as completions of one another. Is that maybe philosophically the reason why A1 homotopy invariants can't distinguish between them? So if we had a formal proof of this statement, then maybe one could be hopeful to think that maybe that's the underlying reason. But as it stands, the reason that it's there is only because we can't prove it without.
So this example was just saying that you cannot always find such a grading.
Exactly. So exactly. So I can't apply it to just any algebra. So it's a necessary thing there that does restrict us, and restrict us in the statement we can make at this point. Yes. All right. So let's talk about this class of invariants. So an A1 homotopy invariant is a functor E from DG cat K. So this is the category of small dg categories over K. And dg functors. So it goes from here to some triangulated category T. And it satisfies some things. Satisfies 3 axioms. And the first axiom such that first axiom.
You mean a single triangulated category, or you mean the category of all triangles?
No, I go to a single triangulated category. That could be a derived category of vector spaces, it could be spectra. Alright, so such that first E inverts Morita equivalences. So now we ask for that to be an analytic invariant Morita equivalences. So it takes a Morita equivalence and sends it to an isomorphism. The Morita equivalence is just a DG functor, so it inverts Morita equivalences, i.e. the DG functors. So DG functors F such that the base change star from perf of A, so the pre-triangulated hull of A, perf of A to perf of B, is a quasi-equivalence. Right, so in particular, our invariant cannot distinguish between a DG category and its pre-triangulated hull. Good, so keep that in mind maybe for the next axiom, if you want. So the next axiom ensures that it's a localizing invariant. The main giving axiom for localizing invariants, which says that E sets short exact sequences of DG categories. You can pretend they're just perf of those. Sends that to a triangle.
So it means co-fiber sequence? I mean,
it means that if you take the derived category of perfect complexes of that, that's going to be a localizing sequence. Basically, because you just assume everything is already perf of it. That's the idea.
Question. So your theorem is about the additive range on the singularity category, is that right?
So, say that again.
You have an exact sequence like this with the singularity category, right?
Yes, you will.
And so your theorem is about the value of the A1 invariant on the singularity category?
Yes. I mean, like, okay, so I have planned this today as that being the result, and I can actually from that, as an application, say something about the singularity category.
But it's not equivalent. Okay. To this.
Well, it is. Well, if you want, it is equivalent. Yes, it is equivalent. I mean, like, I could just have added some stuff to that theorem and included a statement about the singularity.
So to make it completely equivalent, you mean that the map induced by the inclusion?
No. Yes. Well, I guess that's what you're asking, right? No. That I'm not saying that. I'm not saying that. At the moment, and we're going to see that later, it's actually not in general going to be true. So this is not in general an isomorphism that's induced from the inclusion. Yeah. And we're going to talk in an example at the end about what the induced map. Well, I mean, maybe you can already guess because we already had an integer matrix on the board. And maybe that has something to do. Who knows? Alright, so it sends that thing to triangles in T. A, B, and you get the gist, right? B of C in T. Fantastic. So that's that is that. Hausdorff homology satisfies these first two axioms. It is a localizing invariant. It's better not satisfy the last one, right? Else our theorem is wrong, as we've just seen from our example. And it doesn't. I mean, I guess Hausdorff, Constant, Rosenberg would be would be the reference. Anyway, what is it? Should tell you. So that's the name-giving axiom for an A1 homotopy invariant, which tells us that you can't tell the difference between A1 and the point. Right? And that's how do we phrase that algebraically? So E inverts the inclusion, so the natural canonical factor, which goes from A to tensoring over K with the polynomial ring, and we view this, so this is the polynomial ring, see that, and we view this as a DGA concentrated in degree 0. Space, yes, as a DPA in concentrated in degree 0. So what this does is just to all the Hom complexes in every degree, we adjoin a variable t. So our invariant cannot tell where we do that. And that's quite important, right, for the result to hold. So if you want some examples, just look at the time. Yes, if you want some examples of.
Well, that means you have a DD category, so you base change that, or push forward along that map. Because you're starting with a category and getting out another category.
Yes, yes. Yeah. Exactly. Okay. So examples of an A1 homotopy invariant would be homotopy K theory. Also, like periodic cyclic homology. Non-example would be Raedschelders. So we have interesting invariants that satisfy this. All right. And now let's talk a bit more about this nuisance, or maybe this blessing for today, of having this gradability hypothesis. So just kind of quickly want to tell you a bit about what the idea, why we really need it, what the kind of core idea of the proof. So the point is, somehow, the point of having this gradability is that if we put a grading on our algebra, it rigidifies the situation massively. So idea so putting a grading allows us to rigidify. I do not believe that this is a technical term. Put it in quotation. All right. So what do we mean by that? Maybe let's look at a. Will we? Won't we? I mean, yes. So basically, it's just right. We get a bunch more objects now. We get a bunch more modules because we put a grading on it, which can shift them around in any degree. Like, just think of the simples, right? Even if you just over the dual numbers, where you just had one simple, when you grade it with epsilon in degree 1, you're going to spread out your simples, right? You're going to have a simple in every degree. But that spreading out is actually a blessing, because it means that if we now look at x between those, because if you look at the projective resolution of your simple, then suddenly to make sure that all your maps are degree 0 maps, you'll have to increase the degrees that your projective lives more and more the further you go along. So you kind of spread out your x across different degrees, making it much more rigid. Okay, so grading kind of rigidifies the situation. So we kind of deal with much fewer maps, and that's the beautiful, very helpful result. We have this lemma, which I guess is a classical result by Hubler. That is how it's referred to in a paper of Tabuada and Van den Berg, with a proof of the statement can also be found. And this tells us that if we have a one homotopy invariant, and A is a M0, so non-negatively graded DG category. So what does that mean? That just means that every Hom complex in A has a grading, so that is isomorphic as a cochain complex to some pieces as complexes. So that means that the differential preserves the grading here, such that this is compatible with composition of maps. Right. So that's what it means for a DG category to be graded, and of course non-negative, right? So n is bigger or equal to 0. If you have that, then not just if you spread out all the stuff across degrees, but actually now E can't even tell the difference between you and your degree 0 partial. So this is an isomorphism. And we use that result twice. So we need the gradability. So we get on stuff where we get some grading from that. Yeah. So that's kind of the reason we have the hypothesis here. So yeah, makes stuff nicer. So let me, to come back to Valen's question, let me talk a bit about an application. And this kind of goes back to the question, well, they're isomorphic, right? But how exactly do they relate? Like, what's the inherited map? And this is not necessarily isomorphism. And so we have lambda, our fixed finite dimensional algebra, so let lambda admits the necessary grading, so let lambda admit a non-negative, I'm just going to call this a non-negative semi-simple grading. Not just me. Semi-simple grading. Right, so we have that, as Merlin pointed out, right, we have our inclusion here. And the question is, what kind of map does this induce between the E of those things that I told you are isomorphic? Now there's one thing I kept a little bit of a secret, well, for no reason except that I had fun doing that. So we don't just know that these are isomorphic, we know what they are. And in fact, E, you shouldn't write a big arrow, comes later, E of D perf, which is isomorphic to E of dB lambda. So E is just now again any A1 homotopy invariant. That thing is just n copies of E evaluated at the base field. And n again is, as before, the number of isoclasses of simple. So if you work with a basic algebra, just indecomposable summands of lambda 0. Okay, so we actually know what that is. So if we apply E, we're going to get a map from n copies of E of k to n copies of E of k, but this is not, in general, an isomorphism. Again, I come back to what I said earlier, you might already have a hint. We had a n cross n matrix on the board before, the Cartan matrix. And the point is, I mean, this requires a little bit of work here, but the point is that actually it's enough to just look what homotopy K theory does. Like, if you know what homotopy K theory does, you can then kind of like do a little bit more work and revert it back to just computing K0 of this map. And that's going to give you the map for any A1 homotopy. So some magic happening here in the background, but that map is just given by the Cartan matrix. So, you know that if your Cartan matrix is invertible, if it has, if it's invertible, that means that your singularity category is an A1 homotopy phantom. Every A1 homotopy invariant is going to just think it's nothing, it's trivial, right? So that's kind of in a way, you can think of this as a neat way to come up with examples of A1 homotopy phantoms if you want to do that. Why wouldn't you? So let me just end, because I did promise a quiver. I did promise Karen a quiver. And everyone else who likes quivers. So right, if we work with if we assume that our finite dimensional algebra is basic, then I can just write it as a path algebra of a quiver with relation. And somehow I can just I can just try to cook up some examples that are going to have, I mean, if I have something like that, it's not magic to write down the Cartan matrix. I can try to cook up some examples with invertible Cartan matrix.
We stole 5 minutes from you at the beginning, playing the cards. So
well, but also we were all waiting for the conference dinner, right? So I'm aware of
lost track.
So, an example, maybe I can make sure I have it in front of me. Yeah, I have. Let's look at a quiver with two vertices, with 3 arrows here, and a loop here. And well, I should impose some relations to make sure this is finite dimensional. I'm going to assume that radical square is 0. That is, whenever I compose two arrows, then I get 0. Now, for those of you who are incredibly quick at calculating, and I know some of you are, I just want to say that that thing doesn't have a convertible Cartan matrix. But I just want to tell you how we can just like nicely write down the Cartan matrix here. So I said that the columns of the Cartan matrix are just the dimension vectors of my indecomposable projectives. So I want to write down the indecomposable projectives, and I can write this down as a Krüger representation. And then all I have to do is count the dimension of the vector space at vertex 1 and at vertex 2, and that's going to give me the dimension vector. It's going to give me a column in my Cartan matrix. And in order to do that, to compute P1, I just look at paths ending in 1, so I'm working with right modules. So how many paths are there starting in 1 and ending in 1? There's only the lazy paths. That's just going to give me a k here. How many paths are there starting in 2 and ending in 1? There was none. It's going to give me a 0 here. And, well, you know, I guess you can figure out what the maps are. We don't need them though, if you don't want to. Alright, good. So, what about 2? We do the same thing. We look at paths ending in 2 now. How many paths are there starting in 1 and ending in 2? They're precisely 3, 1 for each arrow, because I can't compose with the loop. Compose with the loop because that's a trivial relation. So I have k3 here. And here, how many paths starting in 2 and ending in 2? I have the lazy path, but I also can go loop once. So I have k squared here. And the Cartan matrix is thus given by 1, 0, 3, 2. And now some magic happens. I look at the trivial extension algebra, which as a vector space is just lambda plus its dual. Now with, I don't want to write down the multiplication, but the multiplication just ensures that if we restrict it to d lambda, then it's trivial. So I can do that. And basically what I'm going to get from that here, that the indecomposable summands of that are just the injective modules, which I can create just dually to my projective modules. So what I get as the Cartan matrix of lambda tilde is just the Cartan matrix plus its transpose. And that looks pretty promising because that is 2, 3, 3, 4. And the determinant of that thing is 8 minus 9 is minus 1. It's invertible, and we know that the singularity category of lambda tilde. I should say here, with the induced enhancement coming from the bounded derived category, so that's important, I kind of glossed over this a bit, is an A1 homotopy. I just realized I didn't tell you anything about the singularity category, but you'll have to do with that because I guess you're out of time. A1 homotopy. Phantom. And just last, like kind of just a little bit of a treat because I think it's fun. In fact, that thing also has vanishing K0 that follows from a result by Tachikawa and Wakamatsu. And so if you were interested in something that's not trivial but has vanishing K0, that is such a thing. All right, thank you.